Hello React Native developers, in our last video we've built some fun SVG animations. Well, in this video we are adding the third dimension. Guys, I hope you are well. William here, recording from beautiful Zurich, Switzerland. In the past few days I've been working on building 3D projections between SVG and Reanimated 2. And in this video, I would like to show you how I've built some of these projections and how I've recreated some of the animations from the ZDog library with tight integration between gesture handler, SVG, and Reanimated 2. Why on earth would we want to do that? Well, for fun, of course. It might also have some practical aspects down the road. And also I've noticed that every time we explore the 3D world, it helps us harness and understand better the two-dimensional world. And in the last video where we've built a pseudo 3D engine in React Native, it helped us identify bugs such as SkewX not working on Android. So it helps us with the 2D world. And these 3D explorations all started with complex 2D use cases, most notably the pinch to zoom feature, where we needed to accumulate across time complex transformations. And we used linear algebra in order to do this. And discovering this new mathematical tool made me want to explore the third dimension. And in our last video regarding 3D transformations in React Native, link in the video description, we projected 4 points representing the 4 corners of a React Native view into the 3D world, and then finding the 2D transformation for the React Native view that will make the corners of the view match the position of the projected points. This process is called homography, and at the time, because we were using Reanimated v1, the algorithm we were using to calculate the 2D transformation was super crude. Now we could run, thanks to the animation worklets in Reanimated 2, more complex algebraic functions on the UI thread, most notably calculating the determinant of a big matrix. And so that would be fun to redo such a process in Reanimated 2. Why not use libraries like free.js? There might be, again, it's really for fun and also for us to learn about linear algebra and building simple things to understand down the road the more complex things. But it might also have some practical use cases where we want to apply complex transformations to native views or have a deep integration between the gesture handler and the SVG or React Native view. In this video, I would like to show you some of the techniques I've used in order to build a pseudo 3D engine between Reanimated 2 and SVG. I took inspiration from the ZDog library, and this library is super interesting because for some simple shapes, it does like an ellipse or a box, it does the regular 3D workflow, projecting 3D points onto the 2D space. But for more complex shapes, it plays a trick that is quite interesting, which is to project key points of the shapes from the 3D world to the 2D world, and then calculate the remaining of the shape based on these projected points. So not your typical 3D workflow, but by playing this trick, we can build some fun and interesting examples. Redash ships a process transform 3D function, which is equivalent to process transform from the React Native implementation, but done as a worklet. So you can execute it on the UI thread. You give it a list of transformations, same API than the React Native API, and as an output, you get a 4x4 matrix. You can use this matrix to go from a 3D vector to a 2D vector. And this process is explained in details in our previous video about 3D transformations, link in the video description. So using this function from Redash, I would like to show you how we can build simple 3D shapes just by projecting the points of the shape onto the 2D space. And then we're going to look at a more complex example where we calculate the projection of key points from the shape, and then we calculate the remaining of the shape based on the projected points. Before we get into it, one thing, if you're interested to learn the fundamentals of gestures and animations in React Native, I hope that you will check out my online course at startreactnative.dev. My goal with this course is to provide you with all the tools and knowledge necessary in order to build delightful user experiences that will run at 60 FPS even on low-end devices. So if you're interested to learn the fundamentals, I hope that you will check it out at startreactnative.dev. Let's build our first 3D shapes. So I'm going to show you a couple of components which I created. The first one is, the names are very uncreative. The first one is called ZSVG. Is going to be the Canva container. So we pass the dimensions as property. So we have here the width and the height of our Canva. And so there are some simple shapes I can show you. So for instance, Z ellipse. And the Canva goes, so we give it dimensions from our React Native Canva. But internally, to simplify things, it's using a Canva of coordinates -1 to 1. And so here, if I want to set the radius on the X, we're going to make it a circle first. So if I want to set the radius on the X axis, maybe I can use 0.4. And for the Y axis, so let's make it a circle. So same radius on the X and Y axis. So we have stroke width, which is 0.1. And stroke, we can just pick any color. I don't know, let's take the first one. And so here you see we have an ellipse which rotates in 3D. So let's look a little bit in our components to see what's going on. So we have two components, the Canva and the shape. So in the Canva, so we display the shapes, but we have this camera component. And we use a context for the camera and the Canva because this is going to be used by the children to do the projection. So the camera component is very simple. It's a overlaid transparent view. We have a pan gesture handler, and we calculate the X and Y rotation depending on the position of the finger. So if we move the finger on the Y axis, we trigger a rotation of the X axis. And if we move the finger on the Y axis, we trigger on the X axis, we trigger a rotation on the Y axis. And we need to convert from points. So let's say what are we doing here? So if we go from, let's say, the complete width of the screen size, this triggers a full rotation on the axis. And same for the X and Y axis. And then on end, we add some decay. So depending on the velocity, we continue the animation. So that's what the camera does. We apply the transformation to get the 4x4 matrix. Because it is set in the context, it can be available from child components. And so let's have a look at the ellipse. So we get the radius X and Y radius as parameters. We draw the shape. So this is a Bezier curve. So in Redash, we normalize paths to be sequences of Bezier curves. And here we express the ellipse as a concatenation of 4 Bezier curve, and add arc3 converts the parameters of a quarter circle into a Bezier curve. And we actually, in a previous video, also looked at how to convert from a circle to Bezier curves. And using Bezier curves instead of the shape directly can enable us to do path morphing, or also to treat basically different shapes, heterogeneous shapes, homogeneously. And then, so we calculate the path and we pass it to this child, which is using the camera to transform plus, so it has a transform property in case we want to add some transformations, which we're gonna do. So that gives us the final transformation matrix, and then we project every single points from our Bezier curves to get the projected shape. We serialize it as an animated property, and that gives us what you're seeing here. And then we can also animate the progression of the shape, which is this example here, where we have these 3 ellipses, and then we can just rotate them in any directions. So let's go back here to our ellipse, and we can add another component, a rectangle, so Z rectangle. And so I'm gonna use here different color and width, let's say 0.8, height 0.8. So now they should be, so they are exactly on the same plan. And you see even here you have some Z, what we call Z fighting, because they have the same Z index. But we can now move them onto the Z axis. So I'm gonna use the transform property here. So I'm gonna add a transform. So I'm gonna add translate Z, and let's say minus 0.2. So now one should be in front of the other. You see it here, right? So there is no more Z fighting. I can move maybe the other one forward. Add some fill maybe to the rectangle. So you see here, we have a nice pseudo 3D transformation. And potentially we can use, so here we didn't use perspective in the transformation. We can use the perspective transformation as defined in the React Native implementation. So if I go here to perspective, so which is what we call weak perspective, which is simply gonna make closer object look bigger or further object look smaller. But potentially, I guess we could try to build some more complex perspectives, such as the ones you see in OpenGL systems. And another example of such simple projections is the cube. So you see here, if I go to the cube example, so we have the Z box. So a cube or a box has 8 points, right? So these 4 points here and the 4 points at the back, which we have here, which we project here. So we have the projected points here. And from these projected points, we can calculate each face, the 6 faces of our rectangle. And we do this here in order to only project 8 points. So here, potentially, there is a lot of duplicate points, which we don't want to project twice, just as a small performance optimization. In ZDog, there are simple shapes which are projected using the same method that we've just seen. But then there is another category of shapes, which is super interesting. And so the cone, the cylinder, and the hemisphere. And actually, we're going to look at the cone, but you will see quickly, I think it's going to become apparent that these 3 shapes are kind of the same, but a little bit different. And these projections are done a bit differently. Here we project some key points of the shape, and then based on these projected points, we make some other calculations. In the case of the cone, we have the base of the cone, you see, which is a circle, which is projected onto the 2D space to become an ellipse. And then we have the apex of the cone, which we're also going to use using the projection to calculate its position. Once we have these two projections, we are going to calculate the tangents to the ellipse to build the triangle. And that is going to give us this 3D cone. So if I go to the code here we have our circle, which is projected to the 2D space to become an ellipse. And then we have this red point, which is moving here, which is the projection of the apex. So we have the 3D projections we need. Now, from these projected points, we need to calculate the tangents from these tangents of the ellipse that go through the apex. So these points. How we calculate these tangents? First, we need the parameters of our ellipse. We have the 4 control points which we used to draw the circle. So here the circle is calculated as a concatenation of 4 Bezier curves, but actually here it doesn't matter. Basically, we know the radius of our circle, that's all that matters. And we need to calculate A and B. And I was scratching my head on how to calculate the parameters of our ellipse. So if we go to the ellipse is defined as this equation, and A and B, so A is a semi-major, so it's a radius here on the x-axis, and the B is a semi-minor axis, which is this value. And we know a couple of things. We know that actually, you see, if I run the projection in any position, one of the radius is always the radius of the original circle. So we have the value of A. A is always, so the semi-major axis is always equal to the radius. I could draw the circle of radius R here, and you will see that it always touches the points of the circle. And then to calculate B, I was scratching my head and I found this figure, and this made me realize that this is exactly what we have right now. So these here, 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 here are the points we know about. These are the projected points, so the red points that you see here. And what we want to calculate is a semi-major axis. So this one here, and this one here is equal to R. And in the article from Wikipedia about the ellipse, it gives us the formula to calculate B. So you see here, again, we have our control points. A, we know, is equal to the radius of the circle, and we want B. And there is this theorem of Apollonius that tells us that this length here is equal to this length here, which means that C1, so using the Pythagoras theorem, C1 square plus C2 square equals A square plus B square. We know that A square is R square, so we know that B is square root of C1 square plus C2 square minus CA square. And then we need to calculate the tangents of the ellipse based on these two parameters. From the Wikipedia article, we know that this is the formula of the tangent of an ellipse, and we want the two tangents that go through the apex, and we know that the apex is of coordinate, so x0 is 0, and y0 is the value we have once we project the apex. So we know y0. So we can calculate y from here, because here, so x0 equals 0, so that gives us y0 divided by b square times y equals at 1. That gives us y equals b square divided by y0. So now we can substitute y in the equation of the ellipse because we know we want the 2 points in the ellipse for this y value. So again, based on the equation of the ellipse, that would give us x squared divided by a square plus y square equals b square equals 1. This is the equation of the ellipse. We can substitute y to find x. So that would give us x square divided by a square equals 1 minus y square divided by b square. And that gives us x equals, so we multiply by a square and this and everything. So we multiply by a square and everything square root. So square root of a square would be a, and then square root of y square 1 minus y square divided by b square, and we can even substitute directly y by this value here. So that gives us y, so 1 minus b square divided by y0 square divided by b square. Before we get into the code, we can check if our formulas are correct. So here I have the formula of an ellipse. I have the b and a parameters, which we can vary to any random values. And we have y0, which is going to be the coordinate of the apex. So here we don't see it here, but we have a point basically right at 6. So x equals 0 and y0 equals 6. And so we can enter, we calculated that y equals b square divided by y0. Oops. Sorry. Divided by y0. So that we know that the tangent is going to be at these points, but we need to calculate the x coordinate, and we know that x equals a times square root of 1 minus, so b square divided by y0 square. Oops. Divided by b square. We've made a mistake. It's poor. You see, because here I see it's not, so the result is not correct. And I see that I miss was b power 4. And you see here, this is the point we're looking for. And we can copy it here with minus a. And so here we have the two tangents that go through the position of our apex. Of course, here we use x equals 0. We know that the apex is rotated. We're gonna apply the rotation afterwards. So we know that a equals r, but now we are working here with the projected shape. So we change the scale of the coordinate system. So I'm gonna do scale.x times divided by 2. And this is because we go from not 0 to 1, but minus 1 to 1. So we divide by 2. So we have a, and we know that b equals square root of c1 square plus c2 square minus a square. And we know that c2 is this point. So I'm not gonna reproject it again. I'm gonna use the projected version directly. So which is path.move. So that's the first point. So this requires me actually to know, I know the internal structure of path, which is this object here. But if you don't know how it's represented internally, you can simply do the projection of the point directly, right? Like we do here for Apex. So I could use project of the point directly, but here I'm saving one computation. And so C1 is path dot curves. So the first curves destination point. And so it's not scale, but Canva. And these are vectors. So we want the distance from the origin. So I'm going to use dist2d for that. So that simply calculate the Euclidean distance of a vector. And here we only look at the first two dimensions. Again, here, this you can find again through the Pythagoras theorem. So now let's calculate the tangents. So we know that, so if we go back here, y0 is y is b squared divided by y0. And y0 is the distance of the apex from the origin. And so again here, right, we ignore the rotation. The thing is rotated and we rotate after. So y0 is the dist2d of apex. So we have y is equal at b squared divided by y0. And that gives us x. X is, so this formula, a times square root of 1 minus, so you see that this expression here is y square, right? So b power 4 divided by y0 power 2 is y square. So that would give us y square divided by b square. Now, if y0 is less than b, the ellipse is not visible. So we're going to return. We're not going to be able to calculate the tangents because the point is within the ellipse. So we're going to, and anyways, it means that the apex is invisible. So we don't need to calculate anything. So I'm going to return apex and then points. So 0, 0, z is 0. Doesn't matter. Here, up, and then apex. I mean, yeah, I just can return something empty here. And if the ellipse is visible, so here we have x minus x. This one is the apex. And here we have y. And also depending on the sign of y. Let's draw so let me remove these debug things here. And let's draw the apex. So I'm going to do a vertex. So vertex simply shows you the polygon from a list of points. So points, fill. So we have body color. And so we have this one. So let's do points, use derived value. And so we have data.value.points. Up. So here we are getting some, not a number, if y is great, y0 is greater than b. No, it doesn't make sense. We miscalculated something somewhere. And I think here it's, I need to do this on the projected path, not the, here you go. Not, I was working with the 3D path, not the projected one. So you see, it actually works here. We just need to match the rotation of the ellipse here. And the rotation, because we've made the calculation like this here, we need to rotate to this corner, so to minus pi divided by 2, and add this angle made by the apex. And here we know that this coordinate is a tan of y divided by x, right? Every time we want an angle in all our previous videos, every time we want the angle from the coordinate, we know that on the Euclidean coordinate system, it's going to be a tan of y divided by x. So the rotation on the z-axis is minus pi divided by 2 plus a tan, so a tan 2 of apex.y, apex.x. And here we're going to rotate each point by RZ. So you see, we're cheating completely to calculate the 3D projection, but it should give us an interesting result. So, oh, no, it's minus math pi divided by 2. So that starts to look good. Now we can interpolate the color of the base, and this is why here I use process color. So if we are seeing the base from face, it means that the apex is the z index, the z value of the apex coordinate is negative. So if data.value.apex.z is less than 0, we see this little ellipse from the face, so that would be CO1, if not CO2, color 1, color 2. So you see here, and the tangents don't look correct, but I think I know why. So here we are looking at it. So we play, you see, we play many tricks to make it look like a 3D shape. We do some projections, we calculate the remaining, we also play with colors to give the illusion of a 3D shape. But here, let me check, looks good. Isn't that cool? Guys, I hope you enjoyed these examples. We are mostly doing these experiments for fun and also for the love of math, but maybe you have some concrete and practical use cases for such techniques. If so, please let me know in the comments below. I am looking forward to talk to you soon, and until next time, happy hacking.